Hello. In this lesson, we are going to be introducing you to crystallization, which is one method of separation that we do use in chemical engineering unit operations. Crystallization, broadly speaking, is the formation of solid particles within a homogeneous phase. The homogeneous phase here can be a fluid such as liquid or vapor. In a situation where you have the formation of solid particles in vapor phase, such as snow forming in air. In the liquid phase, it can occur both in the liquid melt or in liquid solution. In the liquid melt, crystallization is employed usually in the manufacturing of glass, where you have a solidification of glass from the liquid glass. In liquid solutions, you have solute crystals crystallizing from the liquid solution. In this course, we are mainly going to be focusing on the last one here, which is crystallization from a liquid solution. Before we proceed, let's just look at some definitions and considerations. In crystallization from a solution, the two-phase mixture of the mother liquor, which is the solution body, and that of the crystals is termed the magma. The important factors in crystallization operation include crystal sizes, the uniformity of the crystal size, the yield of the crystals, the purity of the crystals. For these reasons, it is very important to control crystal size distribution as the prime objective when you are designing or operating the crystallizer. The crystallization process comprises four main stages. The first and necessary condition is that the solution must be in a supersaturated state. This means that the solution must be at a concentration higher than the solubility at that given temperature. The second step is that nucleation is required to occur. In crystallization, nucleation can occur in two ways. The first is the birth of new crystal particles from molecules coming together and forming crystals. And then the second is where crystals are added into the solution as seeding crystals. After nucleation has occurred, the subsequent step is that of the growth of the nuclei into larger crystals until the equilibrium between the solute crystals and the solution is attained. The last step in crystallization is that of recrystallization. If you give the crystals and the solution more time, then the crystals start to recrystallize by reorganizing the molecular structure, the crystalline structure, to a lower energy state. This happens without changing any crystalline volume mass. Basically, at this point, the crystallization is not really occurring. It's just the crystal changing its crystalline structure. Let us look at the definition of solubility in the crystallization process. A solution is a solute dissolved in a solvent. A solute in a solution will have a given solubility at a specified temperature. The solubility is the concentration of the solute at a saturation point. This is the maximum amount of solute that can dissolve in a given amount of solvent at a given temperature. The solubility or saturation is dependent on temperature, as indicated in the picture shown here, where at this temperature your solubility will be a value somewhere here, and then as you increase the temperature, your solubility increases. As you can see, at this point in temperature here, your solubility will be significantly higher compared to that at lower temperatures. A solution with a concentration below the solubility value, which is below this blue line, is unsaturated and will allow more solute to be dissolved until it gets to saturation, to a point where saturation is reached. If you have a solution here, for example, you are dissolving 100 grams of the solute into a given amount of solvent, and once 5 grams has been dissolved and you are at the point here, which is unsaturated, meaning that you can dissolve more of the solute into the solvent. Dissolving more of the solute into the solvent to get to a saturation point. Here we have now attained saturation where we have equilibrium between the undissolved solute and the solution. At this point, we have dissolved 91 grams into the given amount of solvent, and we have 9 grams of solute that is undissolved, that is now at equilibrium with our solution. If we take that saturated solution and we increase the temperature from 25 degrees to 50 degrees, you can see that we are moving horizontally on our graph. We are moving horizontally on our graph. We are changing the temperature and keeping the concentration constant. We are moving away from the saturation line. At this point, our solution is now unsaturated and can allow further dissolution of the solute into it. And the 9 gram that was undissolved now gets dissolved. We still have an unsaturated solution, meaning that we can dissolve more solute into it to get to saturation. If we take this unsaturated solution and cool it back to the original temperature of 25 degrees Celsius, we are crossing the saturation line into the supersaturated phase now. At this point, we have a supersaturated solution. Allowing more time for the solution, crystallization starts to occur, and the crystals will form until we are back at saturation where we were now with that 9 gram of crystallized solute in the solution. At this point, we are coming from the supersaturated side of the solution. We have 9 grams of crystallized solute in equilibrium with our solution. Initially, when we were coming from the unsaturated side, we had 9 grams of undissolved solute in equilibrium with our solution. As we have stated, equilibrium in crystallization is reached when the solution is saturated and our solution is in equilibrium with undissolved solute or with crystallized solute. Saturation or solubility is a function of temperature. Most materials have solubility that increase with increasing temperature, as you can see in our plot here, for sodium nitrate, potassium nitrate, ammonium chloride. For most common solutes, the solubility increases with increasing temperature. A few substances, however, have solubility that is unaffected or affected only slightly by temperature, as we have here our common salt, sodium chloride, not changing much with the change in temperature. The solubility is not changing much with the change in temperature. Other solutes have what is commonly known as inverted solubility curve, meaning that their solubility increases with decreasing temperature, as you can see that of ammonia here in water. Looking back at solubility, saturation, and equilibrium, any solution in the blue region here is in the unsaturated phase, meaning that the solution is stable and crystallization cannot occur. If you put any more solute crystals, they will dissolve into the solution. At the saturation line here, the solution is in equilibrium with undissolved solute or with crystallized solute. If you are coming from the unsaturated side and dissolving more solute, at the saturation line, you will have solution in equilibrium with undissolved solute. If you are coming from the supersaturated phase and crystallizing solute, you will have your solution in equilibrium with crystallized solute. Above the saturation line here, the solution is supersaturated. In this region, the solution has a potential to crystallize. In theory, solution above this line will crystallize, will start to form crystals. In the supersaturated phase, we have two phases. The first phase is the metastable zone, and then the second phase is the unstable zone. In the metastable zone, the solution can form crystals. However, spontaneous nucleation does not occur, meaning that without crystals already present in the solution, crystallization will not occur. If there are crystals in the solution, crystal growth continues to occur until you get to the saturation point. This is the crystal growth region of crystallization operations. In the unstable zone here, spontaneous nucleation occurs and crystals form spontaneously without any seeding. In the metastable zone here, crystallization will only occur if there is nuclei present in the solution, either coming from the unstable zone here or the nuclei being put into the solution as a seed. Crystallization only occurs on the pre-existing crystals by growing them. Let's look at how supersaturation can be attained in solutions. The first thing that we need to note is supersaturation cannot be attained by dissolution of solute only. This means that if you are in the unsaturated zone here, you cannot dissolve solute to cross this line. You can dissolve solute only until you get to equilibrium, which is the saturation line. Above that, no matter how much solute you add into the solution, you cannot dissolve anymore. For a situation where you have your solubility increasing with temperature, cooling a saturated solution will cross the saturation curve into the supersaturated phase, hence creating a supersaturated solution. So if your system is that of solubility that increases with temperature, you can have a solution in the unsaturated zone. By cooling it, you can move across to the unstable zone into the supersaturated zone. Another way of creating supersaturation, if your solubility is fairly constant with temperature, such that of a common salt in sodium chloride, and you can see that cooling will not move across the saturation line, as cooling will be going horizontal and the saturation line is also horizontal. So moving along with cooling will just move in parallel with the saturation line. In this, supersaturation can be attained by evaporating some of the solvent from the solution. If you have a solution in this unsaturated zone, you can remove some of the solvent by evaporation, hence increasing the concentration of the solute. If neither cooling nor evaporation is applicable into your system, we can attain supersaturation by addition of the third component into the solution. This third component mixes with the solvent and changing the solvent properties to form a new solvent which has lower solubility of the solute. In this way, shifting the solubility curve downwards. If you had a solution somewhere in this region and then you add the third component, it will shift your saturation line to this point, and now you are above the saturation line into the supersaturation zone.
Let us now spend some time to summarize the methods that we have discussed above that can be used to create the state of supersaturation in a solution in order to effect the process of crystallization. The first method is that of cooling, where the temperature of the saturated or unsaturated solution is decreased, and hence you move across the saturation map, crossing the solubility curve into the supersaturated state. The second is evaporation. Evaporation can occur at a constant temperature, where you move directly vertical, where the temperature of the solution does not change. This can be done using vacuum, or you can also increase the temperature of the solution and then boil off some of the solvent in the solution. The other part would be you can also effect evaporation by using dry air, which will evaporate some of the solvent from the solution. In that situation, you will have a evaporation line similar to the one shown here in the graph, where your temperature of the solution will decrease slightly as some of the solvent is evaporated. The third method is the use of a third component, which is an antisolvent. The antisolvent does not necessarily change the concentration of the solution. What the antisolvent does is it shifts the saturation line, it shifts the solubility curve of your solution. If your concentration was here on the saturation line, meaning that there's still no crystallization. If you add an antisolvent, the saturation line shifts below, and then hence you end up in the supersaturated state above the saturation line. The other method that you can use is precipitation. Crystallization involves two main steps, which are nucleation, which is the birth of new crystal particles, and the growth of those crystal particles to macroscopic sizes. The crystal size distribution is determined by the interaction of the rates of these two steps, which means that if your rate of nucleation is very fast and the rate of growth of crystals is very slow, you will end up with lots of crystals which are very small sizes. And if the rate of nucleation is much slower than the rate of growth, you will end up with fewer crystals but of larger size. The driving force for the rates of both of these steps is determined by the state and the degree of supersaturation. Keeping in mind that nucleation and crystal growth cannot occur in the saturated or unsaturated state. You need to be in the supersaturated state. Saturation is measured as a difference between the concentration of a supersaturated solution in which the crystals are growing and that of the saturated solution that will be in equilibrium with crystals at the end of crystallization. These two phases, the supersaturated phase and the saturated phase, are nearly at the same temperature. The concentration may be defined in mole fraction of solute, here denoted by Y, or in mole of solute per unit volume of solution divided by C. The two supersaturation definitions are indicated here by the two equations as we have stated, where delta Y is the supersaturation in mole fraction of solute and delta C is the supersaturation in moles per unit volume of solution. Those two definitions of supersaturation can be related by the density, the molar density of the supersaturated solution and the molar density of the saturated solution. However, in most crystallization application, the degree of supersaturation is kept very low, and those density quantities may be considered to be equal and expressed by the molar density of the supersaturated solution. And then the expression above reduces to be supersaturation in mole per volume units equaling that of supersaturation in mole fraction units multiplied by the mole density of the supersaturated solution. The concentration ratio alpha and the fractional supersaturation S are given by the equations here above. Keeping in mind that the fractional supersaturation S is usually kept very small, and when given as a percentage is usually less than 2%. As a fraction, it will be less than 0.02. When the solubility increases strongly with temperature, supersaturation can be expressed as temperature difference instead of the concentration difference. Please keep note that in this graph, the x's are swapped. The temperature is now on the y-axis and the concentration is on the x-axis. The unsaturated phase is now above the saturated line here, and the supersaturated phase will be below the line here. Consider a supersaturated solution at point D with temperature T. As crystallization occurs towards saturation, the state of the solution moves towards point A with temperature Tc. This is because during crystallization, heat is given off and the solution heats up slightly, and hence the temperature Tc is greater than that of the original temperature of the solution, providing the driving force delta Th. Delta Th is usually very small and is around the value of 0.01 to 0.02 degrees Celsius. Supersaturation alpha is normally calculated using the bulk temperature T, using points E and D, where we are assuming that there's no temperature difference and we are moving along this horizontal line. Point B represents the saturated solution with the same concentration as our supersaturated solution D and with temperature Ts, moving vertically from point D, keeping the the concentration the same and just changing the temperature. And point C represents a solution with the same concentration as our supersaturated solution and with temperature similar to our final saturated solution temperature after the temperature has increased slightly due to the energy from crystallization. The supersaturation potential is given by the line segment AC, which gives the path of saturation from our original solution and concentration and temperature to the final solution concentration and temperature. The equivalent temperature driving potential will in this situation be given by line BC. If line segment AB is considered to be linear with slope kappa over a small concentration span, the temperature potential can be derived to be the expression given over here, where kappa is the slope of the line segment AB and rho m is the molar density. As we have indicated, delta TH is usually very small, and therefore we can assume Tc to be equals to T. Nucleation is the creation of crystalline bodies within a supersaturated fluid. It can be classified into two forms, being the primary nucleation, which occurs in the absence of crystals, and the secondary nucleation, which occurs in the presence of crystals. The rate of nucleation is the number of new particles formed per unit time, per unit volume of magma, or per unit volume of solids-free mother liquor. This quantity is the first kinetic parameter controlling the crystal size distribution. Primary nucleation refers to the birth of very small bodies of new phase within a supersaturated homogeneous phase. From theory, it is believed to occur from sequences of bimolecular collisions and interactions in a supersaturated fluid that results in the buildup of lattice-structured bodies of crystal. This form of primary nucleation is known as homogeneous nucleation. It is defined as the formation of new particles within a homogeneous phase, uninfluenced in any way by solids form, including walls of the container or any minute particles of foreign substances. Here, homogeneous nucleation happens solely from interactions of molecules within the homogeneous solution. Primary nucleation may also be initiated by suspended particles of foreign substances, and this mechanism is generally referred to as heterogeneous nucleation. Once a nucleus has been formed through nucleation, it is in a state of unstable equilibrium with the solution around it, which means that if it loses units from its structure, it will dissolve back into the solution, or if it gains more units into its crystalline structure, it will grow to become a crystal. Such an equilibrium is unstable because there are also large crystals present in the solution. The small crystals are likely to dissolve, and the large crystals are likely to grow until small dissolving crystals completely disappear. This phenomenon is termed the Oswald ripening. The effect of particle size on solubility is a key factor in nucleation. The solubility of a substance is related to its particle size by the Kelvin equation given over here, where L is the crystal size and alpha is the ratio of concentration of supersaturated and unsaturated solution as we have defined previously, and Vm is the molar volume of crystal. Sigma is the average interfacial tension between solid and liquid. The rate of nucleation is the number of new particles formed per unit time per unit volume, either of magma or per unit volume of crystal-free solution. That rate is expressed here by this expression. B is the nucleation rate, and Na is the Avogadro's constant, and R is the gas constant given in these units, and C is the frequency factor. The catalytic effect of solid particles on nucleation rate results in the reduction of energy required for nucleation. If you can remember, catalysis in chemical reaction, which results in reduced activation energy requirements. In that state, the rate of nucleation is now reduced and given by this expression. Now let's look at secondary nucleation. Secondary nucleation is the formation of nuclei due to the influence of existing microscopic crystals in the magma. And these crystals could have formed from the solution or could have been added into the solution to effect nucleation. Secondary nucleation can, by definition, take place only if crystals of the species under consideration are already present. And since this is usually the case in industrial crystallizers, secondary nucleation plays a very important role on virtually all crystallization processes in the industry. The other most influential mode of new crystal generation in the industrial crystallizer is the contact secondary nucleation, which happens between crystals and the walls or other internal parts of the crystallizer, or even between the crystals and the mechanical agitator. Let us spend a few minutes looking at crystal growth. Crystal growth in crystallization is considered to take place in two stages, where we have the diffusional step, in which the solute is transported from the bulk fluid through the solution boundary layer adjacent to the crystal surface. The usual mass transfer coefficient Ky here applies in this step. The second step is the deposition step, in which the absorbed solute ions or molecules at the crystal surface are deposited into the crystal lattice, increasing the size of the crystal. From mass transfer theory, it is generally assumed that equilibrium exists at the interface of the two faces, which is at the face of the crystal. If it were true in crystallization, this would mean that the concentration at the crystal face would be saturation concentration Ys, resulting in mass transfer driving force being Y minus Ys, where Y is the concentration of the bulk solution, which is the concentration of the supersaturated solution. As we know, however, this cannot happen in crystallization, because that would mean that at the face of the crystal, crystallization is occurring in saturated solution, which we know does not occur. So this will mean that the concentration cannot be Ys at the interface. So we will define a new concentration Y dash or Y prime, which denotes the concentration at the face of the crystal, which we will know that it will be greater than the saturation concentration, but yet smaller than the bulk concentration of the supersaturated solution, leaving the mass transfer driving force to be the difference between the concentration of the bulk supersaturated solution and that of the concentration Y prime at the face of the crystal. The equation of mass transfer can now be written as follows, using the concentration, the new driving force, which is the difference between the supersaturated concentration, and Y prime, which is the concentration at the face of the crystal. We can further define the surface reaction using the coefficient Ks. If we combine the two resistances into one overall step, we can define K, which is the overall coefficient, and then we can write the overall transfer equation as given here, hence defining the overall coefficient as follows. By eliminating Y prime from the two equations above, we end up with the overall coefficient given by this equation here. From shape factors, the volume of any form of shape is proportional to the cube of its characteristic length as given here, where A is a shape factor constant, also known as sphericity. If rho m is the molar density, the mass of that particular shape crystal or body can be given as follows, which is the volume multiplied by the density, further expressed in terms of characteristic length, sphericity, and the density. We can differentiate this mass of that crystal with respect to time to find how the size of the crystal changes with time, and defining dl over dt as the crystal growth rate, which is usually denoted by the symbol G in crystallizer operations. From the shape factors, we know that the surface area divided by the volume is equals to 6 divided by the equivalent length. Therefore, we can relate the surface area to volume as follows. We can substitute the surface area and the rate of growth, or the rate of mass growth, into the overall coefficient equation to obtain this expression. Then we can rearrange this equation to find the rate of growth, or the rate of crystallization equation as follows. The yield of crystals produced by a given degree of cooling may be estimated from the concentration of the initial solution and the solubility at the final temperature, allowing for any evaporation that may occur, and making the solvent and solute balances. For the solvent, in most cases of water here, the initial solvent present is equal to the sum of the final solvent in the mother liquor, the water of crystallization within the crystals, and the water that has evaporated. Most salts that dissolve in water, when they crystallize, they take some of the water into the crystals as crystallization water, and hence that water taken into the crystals, as it has been taken away from the mother liquor, it has to be removed and be incorporated in the mass balances. The crystallization yield in that can be related to the solvent balance by this equation, where W1 and W2 are the initial and final masses of solvent liquor, and Y is the yield of crystals. R is the ratio given by molecular mass of hydrate, which is the crystals that have crystalline water in them, and the molecular mass of the anhydrous salt. E is also a ratio given by the mass of solvent evaporated divided by the mass of solvent in the initial solution. If we do a balance for the solute, we end up with an expression above here, and then we can combine those two equations to give the overall balance, which we can rearrange to find the yield for crystallization in an aqueous solution. From energy balance, we can calculate the quantity of energy required by the system from the initial state to the final state after crystallization, where lambda is given as the latent heat of vaporization of the solvent, Q is the heat of crystallization of the product, T1 and T2 are the initial and final temperature of the solution, and Cp is the specific heat of the solution, which gives